We're going to be doing a lot of drawing in this video, numerical approximation methods with our integrals. Let's start with this problem. Let's determine whether the left-hand sum is greater than or less than the right-hand sum approximation for the function, not given a function, from 2 to 0, with using 4 equal width rectangles. So here's the deal. Let's draw some scenarios. Let's say we have an increasing and concave up function. Our left-hand sum will look like this. Now remember the left, if you remember this from chapter 5, our left hand from 0 to 2 will use 0, but will not use 2. We're going to use A, but we're not going to use B when we make our rectangles. So we'll start making our rectangles using 0, and then delta x in this case, B minus A over n, so 2 minus 0 over 4 is 1/2. So each one of these is 1/2 distance apart. So this is at 1/2, 1, 1.5, and then 2. So our first rectangles are going to be drawn this way. We're going to use A, which is 0, but we won't use B, because if you end up using B, then we end up going further than 2. We go more than our approximation wants. Okay, so notice that this is an underestimate. In this case, that's increasing and concave up. Let's draw another picture, same thing. Right-hand sum is going to use B, but not A. We're going to start with 2 and go this way. And then that puts us at our 4 rectangles. And now notice that that one is an overestimate. So when you have an increasing and concave up situation, the right-hand sum is larger. Let's do another one. Another increasing but concave down this time. Left-hand sum, we're going to use A, so it's going to be 0 again, and not B. That's another underestimate. And then right-hand sum, we use B, but not A. So that means when we want to find our y-coordinates, we would be using the y-coordinate of B, and then every point after, except for A, we would not use 0 in this case, if we wanted to know the height of each one of these rectangles. Okay, so notice that this one is an overestimate as well. So when we have an overestimate, increasing concave down, the right is larger than the left again. Okay, let's do some decreasing. Decreasing concave down. Let's do our left ones again. Left one is the overestimate. And that means that the right one will be the underestimate this time. Notice how it changed? So in this case, decreasing concave down, the left one is greater. So the first two that we showed you, concave up, concave down, they were both increasing and the right side was the greater one. In this case, decreasing, the left side is the greater one. Let's check this one out, see if that works for the concave up as well. So our left, we draw our left rectangles. We're going to use 0 and we're not using 2. We have an overestimate again. And for the right rectangles, we'll be using 2. We will not be using 0. So we draw our line from 2 and everyone after that, but not at 0. Because again, if we use 0, it would go beyond our 4 rectangles and beyond the scope of 0 to 2. Okay, so this one is another underestimate. So now decreasing, the left was greater than the right. So when they were increasing, the right-hand sum was greater. When they were decreasing, the left-hand sum was greater. Let's talk about trapezoids now. First of all, a trapezoidal estimate is the average of the left-hand and the right-hand sum, which is great. And the value of a trapezoid estimate will always fall between the left and the right. obviously, if it's the average. So notice if we have a concave down graph, our trapezoid will be an underestimate. If we have a concave up graph, our trapezoid is an overestimate. Let's talk about these formulas here. So one of these is the trapezoid, one of these is the left, and one of these is the right. And I'll show you the shortcut later. Let's just talk about each one by one. The top one is the trapezoid. And that one always sticks out. It should stick out because you'll see a 1, 2, 2, 2, 2, 2, 1 pattern inside here. So this is our delta x. This is the b minus a over n. And then you're dividing that by 2. The reason is the height of a trapezoid, that's technically the delta x. Because in geometry, you're used to seeing your trapezoids look like this. But in calculus, our graphs look like this. So the height in this case is, all around every trapezoid, it's the part that connects the right angles. And then the bases are the two rays that shoot out from the right angle. So our situation, we have to rotate them up. And the height is always the distance on the x-axis. So that's the distance between the rectangles. So the height is the delta x, and the area of a trapezoid has the 1/2 in it. So that's where this half comes from, this divide by 2 piece. Okay, let me show you why this pattern exists. So the first trapezoid, we have our height here, base 1, base 2. So that would be, this is base 1, this is base 2. Well, half of it. This 2 here occurs because the next trapezoid uses the same line, the same y coordinate twice. We use this was base 2 for the first one, and now it's base 1 for the second one. So we've actually used this y coordinate twice, and that's why that 2 shows up. And it's going to happen again here, because we already used this one. It's going to happen again here. And then notice this one only got used once. So these outer edge ones, the y coordinate here and the y coordinate here only gets used one time. And that is, this is our a value, this is our b value. B is the n number, a is the sub-zero number. So you know what those little numbers mean. Y sub 0 represents a. Y sub n represents b. It's important to know that. So n minus 1 is 1 over from that. And there's a 2 here because we use this y coordinate twice. We use it for this trapezoid and we use it for this trapezoid. And that happened for each trapezoid in between, except for those 2 on the ends. So that's why this one has a 1 and this one has a 1, but every other one has a 2 because we had to use these y coordinates twice for each of the trapezoids that they belong to. So this just kind of sums it up. We have delta x is our height. And remember, the division by 2 is because the area of a trapezoid is 1/2 times the height. So we could write 1/2 times delta x and then times all this stuff here. Same thing. And then y sub 0 is this first line. Y sub 1 would be the next delta x over. And we use 2 of them because it belongs to 2 trapezoids. And then y sub 2 would be the next one. Y sub 3 would be the next one. Again, it belongs to 2 trapezoids. That's why there's 2 of them. And then the y sub n is our b, and we only use that one time. So that's explanation of the formula, and that was our top equation. So that means these bottom 2 are the right and the left. So which one's which? I kept saying over and over when we were doing those increasing, decreasing, concave up, down ones at the beginning, when you draw your rectangles, the left one, you use A, but you don't use B. This is A. This is not B. The right one, you use B, but you don't use A. This is not A. Remember, y sub 0 is A. Y sub n is B in these equations, these formulas. So let's see some pictures. This is a summary of what we did a little while ago. So our increasing ones, notice these are left rectangles. Left rectangles. The y coordinates use A and they don't use B. The y coordinate here uses A, does not use B. The y coordinate here uses A, but does not use B. Same thing. So all of these left rectangles, they use A, but they do not use the y coordinate of B. You don't ever use both. When you do left or right, you'll never use A and B when you use this as a formula. This is just pictures. The next video, we're going to do an example using the formula, so you don't have to draw it. But just remember that, you know, A and B goes this direction in the alphabet. So A is the left one. That's what you're using for your left rectangles. And remember, if it's increasing, 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 these are underestimates. Okay. Here's the right rectangles. Again, this is B here. And notice that we use the y coordinates on B, but we don't use A. This y coordinate, we use every one starting with B and work backwards, but we don't use A. This is B. We're not using A. And then this is the same, B. We don't use A. Oh, and then remember, when it was increasing, these were the overestimates. Okay, so now if you're just looking at the equations, knowing that this is A and knowing that this one is B, that tells you right away that this one's going to be the right-hand side and this one's going to be the left-hand side.